Hi everybody. So today I would like to talk about the effect of shield breaks. So if you add a break to a shield, how much field will it create in the outside? And for this I have created a pretty simple example. So what we have are two boxes which are cable running in between. So the cable in there is a twisted pair wire. It's a 1 meter of cable. Then the twisted pair wire is shielded with a particular shield, and the shield has been modeled to include the realistic transfer impedance. So it's defined as a transfer impedance down here, and this transfer impedance of the shield, so it's a typical braided cable. This transfer impedance has been converted to a thin panel material that we use in a full wave 3D simulation. And then inside the boxes, let me hide this section, inside the boxes, the shield is basically the wire inside the boxes, the cable is unshielded, and each wire is referenced to a metallic plane, and this metallic plane is then connected to the enclosure itself, while the enclosure can be connected to the ground plane. So I use ports here to change the connection impedance, but that will be not a part of today's presentation. Basically these ports are shorted here, and also the shield itself is connected to the outside of the enclosure by a perfect connection. So that's a ring of perfect electric conductor. So we will not look at the effects of the bond impedance. We will look at about what shield breaks actually do. So this is the setup, and then I measure, of course, the electric field by using probes. So I have a bunch of probes just here placed. We will use the ones on basically this one, which is 10 centimeter away, about at the center of the cable. So that's our measurement, and what we will look mostly at is the electric field down here, and also the current flowing through the ground plane, because this is what typically is referred to as being the common mode. And of course that one is a bigger loop and which create a much higher field than the loop inside the twisted pair wire. So this is simulated by the full wave solver, and what I then do on the schematic is I can drive basically the two wires with a differential and with a common mode signal on the one side, which is called L, which stands for the left side, and on the right hand side both are terminated with 50 ohm again to this reference plane, which means we have a 100 ohm termination for the differential mode, and these are just 1 micro resistors. These are the connections of this reference plane to the enclosure, and from the enclosure downwards to the big plane. And what I would like to show you basically in cable shielding, that the main and the biggest, most important thing is what is the way of or how can the current get from the inside of the cable to the outside of the cable. This will be one of the main teachings in today's videos, because you see it has actually the biggest impact. So we can start with a variation which is basically without any shield. So I have removed the shield, and I drive these wires with a differential signal, and I can drive it with a differential and a common mode signal, but right now I'll stick just to the differential signal. So what we see here is, of course, that first of all, of course, the differential signal, it's transmitted. So let's go for the twisted pair differential signal. It's transmitted, so I use 0.5 volt for each wire, so in the sum it's 1 volt. It's transmitted from the left to the right hand side, and at the low frequencies, as long as you see it, it's a perfect transmission. But then of course at higher frequencies we will see some kind of resonance, so it's going up to 200 megahertz over here. So this resonance of course come from the length of the cable. But that's currently not the main point. What we can look at is, of course, the electric field, and this is called what I call here differential probes at 10 meter distance. So that's the 10 centimeter distance of the field, and we get a particular behavior. Let's say a particular value for the electric field when exciting the system with 1 volt differential. Of course, there is a differential to common mode conversion because the system is not fully symmetric, but that's all included in the simulation. We don't need to take any extra steps to include it. We get a particular value of the electric field, and now of course what we want to do, we want to compare it to different settings. So this is the electric field at the 10 centimeter distance, and this is the current through the what I call enclosure, basically the current between the enclosure and the ground plane through this port. So that's also, we get a certain value over here with the unshielded case, which we will interpret later on. So you can see, of course, with increasing frequency, we get a higher common mode, a differential to common mode conversion, and we get also a higher current flowing there. So this is the non-shielded case, which will be basically like our reference. And in the first step, because before going to the real shield, I use a PEC shield. Okay, so the shield is an ideal shield. There is no way for the current to penetrate to the shield. So that means in the end, what we have basically is a completely shielded case. These boxes are made also of lossy metal, which behaves like kind of PEC. So there is no way for the current or for the field to get out of the box. This is ideally sealed. And then when I hide the outer dielectric and the coating, we have the shield. Sorry, where is my shield? Ah, that's the wrong model. Here's the PEC shield. So in the case of the PEC shield, what we have here is also a completely seal. So there is no way for the current and no way for the fields to escape the system. They will always stay inside, and that's exactly what we see in the measurement. So comparing no shield to something which is called PEC shield, you see this is 0, and if we look at the values, it's something on 1 e minus 68. So there is really no current flowing between the enclosure and the ground plane, and obviously there are also no fields on the outside. That's how we would expect it for a PEC shield, but that's of course not realistic. The shield has a certain transfer impedance, so that means there is a way for the current to get from the inside of the structure to the outside of the structure, and this is modeled, like I said, with the transfer impedance, which we converted to this thin panel material. So here's the behavior of the realistic shield, and now things become more interesting. Let's go back to the to the field probes right now. So this is the unshielded case, and this is the real shield. Obviously the shield does a good job, but of course it's not as perfect as it was in the case of the PEC shield, and same also goes for the current now flowing between the enclosure and the ground plane. I have the case of the no shield and the real shield. It's very small, so let's switch to dB. You can see over here, I mean, these very low frequencies, maybe we don't discuss them. Of course, the current flowing between the enclosure and the big plane is much lower in the case of the shield. Of course, obviously that's what we want to do. And right now, just maybe to remember, so when we have this kind of setup, there is only one way for the current to get from the inside to the outside, and this is by means of the transfer impedance of the shield. And now things become interesting when we add a shield break. So I add a shield break to the shield. So that means at one certain section the shield has been opened, but connected by kind of, let's call it a pigtail. So here is the section. You see I have a kind of pigtail. It's a little bit broader. It's not a point-to-point connection, but obviously the shield is opened here. So now the current has two ways to get out. Of course, through the transfer impedance of the cable, but also over here the current can basically get on the outside of the cable. And now there was a big question: what is the effect of this shield break, and how much can we quantify it? And now looking first, let's look first at the current flowing between the enclosure and the ground plane. So this is the unshielded case, this is the real shield without a break, and when I add a shield break, you can clearly see how much of your shielding is deteriorated by adding the shield break, and it's of course pretty significant. We see at low frequencies, when you expect also the inductance of the pigtail not to have a big effect, the effect is smaller, while at higher frequencies it's getting much larger and we are losing about 50 dB of shielding. So the shield break obviously does a bad thing. And if we look at the field probes, of course we will see a similar behavior. So this is the case of the no shield, this is the real shield without the break, and this is the shield break. And obviously we see that at higher frequencies the shield break can basically deteriorate all of your shielding. What's interesting is looking at this lower frequency. So you could see in the current flowing through the enclosure that at low frequencies there was almost no effect. While here we can see that even at low frequencies the shield break is creating a much higher field. And what's the reason for this? I think it's a very interesting finding, which we can see by looking at the fields actually. So what is important to note is that we have measured the electric field at a 10 centimeter distance, which is pretty close to the cable and to the break itself. And let me set up a nice view here. So we cut through the cable. Sorry, have to go up. We cut through the cable and we plot the electric field. And we are at 1 megahertz right now. So basically there where we see a higher field, but not yet frequency dependent. So we are still in this region over here where we see the big jump in the electric field on the outside, but it does not seem to be frequency dependent. And what's the reason for it? It's pretty obvious to see once you look at the fields. Obviously there is of course a leakage of the electric field at the position of the shield break, which makes sense. The electric field, which is between the two inner wires, can leak out at the position of the shield break, and this is the reason why at very low frequencies the current flowing between the box and the plate, it's not changed, while the electric field actually is changed because the field is leaking. And at higher frequencies, of course, when we get an increase of the current, you can see that the electric field will change a lot. Now we have the electric field due to the common mode and plus the leakage, of course, but the leakage is a much smaller contribution down here. So the electric field due to the common mode is much higher, and that's exactly what we have seen down over here at 100 megahertz, where the shielding is almost completely compromised by adding the shield break. So we can now, of course, run something like a parametric sweep. So right now the shield break was 1 centimeter long, and we can take a look at the results here. So this is the current flowing between, again, the current between the enclosure and the ground plane with different shield lengths. So in a very short break of 1 millimeter already costs you, let's switch to dB, can already cost you like something like 20 to 30 dB. Well, then the longer it gets, obviously the higher the current is flowing. And the same we can do also for the electric field in the same way. So unshielded case on top, shielded case is down here, and you can see that due to the shield break and the leakage of the field, which is very close to the position where we measured the electric field, even the fields here can get higher than in the unshielded case. I think very interesting finding. So this is for a 2 centimeter shield break. So obviously a shield break can significantly deteriorate your shielding effectiveness. But I was talking about the main thing is how does the current can get from the inside to the outside. Obviously by the shield break it's easy for the current, but that's not only possibility that's actually there. And what we can do is not, instead of adding a break to the shield, we can add a break to the enclosure, right? So right now the enclosure was completely sealing everything, but when we add a break to the enclosure, basically a hole to the enclosure, and we keep the shield fixed, there is another possibility for the current to get from the inside to the outside. Obviously inside the current flows also on the inside of the enclosure because I have grounded my reference plane to the enclosure. And adding a hole here gives another opportunity for the current to get on the outside. So we have again two possibilities basically. One is through the transfer impedance of the cable shield, the other is through the hole in the enclosure. And when we now look at the currents flowing on the outside, so unshielded case, real shield, and a hole in the enclosure on the backside that I showed you right now, we can see at lower frequencies up to 30 megahertz there will be no current flowing through the hole. The hole is all completely on the backside, so there is not much current. But at higher frequencies it can actually happen that the current itself is increasing. And if we look at the electric fields, so again no break, real shield, and the enclosure with the hole in the back, we see, I mean, it's not as significant, but we lose something like maybe 10 dB of the shielding. So now in this example, the hole was actually in the back where I don't expect the current to flow a lot. So what will happen if I move this particular hole to the front? Some position very, very close to the cable entry itself, where I expect that there is a much higher current on the inner part of the enclosure. So I took the same hole, the same slot that I have created on the backside, and I moved it away from the backside, so the backside is sealed again, and I move it to the front side. And now things become again quite interesting. If we look at the electric field, so unshielded, real shield, hole in the back, which wasn't that bad, so let's get rid of the hole in the back, put a hole in the front. Oh, and you can see, obviously with the hole in the front, your shielding is compromised a lot. Of course, the current can again get on the outside of the enclosure or the outside of the system and will create an electric field. And when we compare the shield break to the enclosure and the hole, of course the shield break is still worse because there is the highest current flowing on the shield, so it's the biggest opportunity for the shield to get on the outside. However, even the hole in the enclosure has a very significant effect, so it's also something like maybe 30 dB. And you see, because the curve goes down, there is no leakage. Our field probe does not report the leakage. Of course there is a leakage from the enclosure, but the field probe does not record it because it's much closer to the cable than to the hole in the enclosure. But you see that at the higher frequencies, by giving the current the opportunity to flow to the outside of the enclosure, there is a significant compromise in your shielding. And be aware of this when you want to measure things, because if you have an enclosure which is not ideal and you measure the electric field due to a shield break, it's not necessarily the shield break standalone you are measuring, because the holes in the enclosure can significantly contribute to the fact that the current can flow on the outside and create this electric field. So obviously one lesson learned from this is when you want to put like ventilation slot holes into your enclosure, don't put them very close to the position where a cable is entering the enclosure. It's much better to put on the backside, as you can see here, where the shielding is compromised, but to a much lower level than when the hole is placed close to the cable entry position. So I think that's a very interesting findings that I wanted to demonstrate to you today, and it brings us to the point that it's always important to look at the complete system to estimate EMC behavior. Just looking at the cables standalone here is simply not enough. We need to include the enclosure and the way the cables has been referenced in order to calculate realistic results and calculate the whole system behavior. And that's what we can easily do. So just as a side remark, that kind of simulation runs in a few minutes on a laptop. That's not a large scale simulation when you need a straight powerful computer. You can run the simulations easily on a laptop and evaluate all these results, even it's full waves 3D. So I hope you have enjoyed something today, you have enjoyed my presentation today, and you learned something about shield breaks and cable shielding. Up to the next time, thank you very much.